Good morning. So last lecture we saw what is the normal distribution, which we wrote the probability density to be f of x equal to sigma square root of 2 pi exponent of minus 1 half x minus mu over sigma the whole square. Now, how did somebody ever come up with this? So if you have a bunch of data, what you first do is to identify the distribution. What is the first step? You take raw data, which is a long sequence of numbers. How do you go there from that to the distribution?
Histogram that you've been.
First, do the binning process, which leads you to a histogram. Histogram, if you want to remember this, think skyscrapers. Okay, so histogram tells you how many of each kind are present. So it also sort of looks like a middle finger. So how many, a histogram tells you how many of each kind are present in the data. So we'll say that between x1 to x2, you have f1. Between x2 to x3, you have f2. Between x3 to x4, you have f3. x4 and x5, f4. x5 and x6, f5, and so on. Goes both ways. So you take the data, you don't have to know anything about it. Just do the binning, separate them into segments, and from the histogram, we fit a function that describes the histogram, and we call it the distribution or probability distribution function. So we fit a curve that describes the data, and that is what we call probability distribution function PDF, and I use the notation f of x per. All these are concepts that we saw. I'm just trying to recap before I continue further. Okay, and as far as continuous random variables are concerned, sorry. As far as continuous random variables are concerned, we have the PDF f of x dx represents the probability of x taking a value between x and x plus dx. And if I want to know what is the probability that x takes a value between x1 and x2, or say a to b, that would be, do you recall from last lecture? What is the probability of x taking a value between a to b? No, it's the integral
Yes.
a to b f of x dx. What is the probability of x assuming any value between minus infinity and plus infinity? That is minus infinity to infinity f of x dx, and this is equal to 1, because this is the sum of all possible outcomes. This has to be 1. Okay, so we wrote this. We also saw what is called as the cumulative distribution function. Cumulative distribution function, or CDF. So remember two terms here, PDF and CDF. CDF, if I write uppercase f of x, This is from minus infinity to that value, f of x dx. So if I write this, if I draw a function for f of x, if I say this is a and this is b, this integral or this area under the curve represents the probability. I'll write here area under the curve gives you probability of x between a and b. This is a very important concept here. With this is what we will solve problems using the handout. Okay, so you have this. If you want to write this integral, probability of a less than or equal to x less than or equal to b, can we write this minus infinity to b f of x dx minus infinity to a f of x dx. Can we write it this way? This is like saying this area in the middle is this area minus this area. Like saying from here this is area 1 and from here this is area 2. This is like saying 1 minus 2. And look at this definition. If I want f of x, that is minus infinity to x, this is minus infinity to b. This is like writing the cumulative distribution function value at b minus the cumulative distribution value at a. This is the summary of last lecture. And using this, we solved the problem towards the end. We are going to continue doing more. With me so far? So for your quiz, these are the kind of questions you can expect. This is the normal distribution, courtesy of Gauss, who came up with this, and that's why it's also called Gaussian distribution. So this is the normal distribution, or its PDF, the probability distribution function. And have you written it so far? I can take a break.
Quiz will be on these three.
On next quiz is going to be Thursday, and I'm towards the end of this lecture, I'll make a list of 4 topics which you have to study, which will be covered through 2 questions. Okay, towards the end of today's lecture, I'll give you those. What are the topics to study? Okay. For the quiz, I will have a smaller set of topics than for the exam. Okay, so the quiz is coming up pretty soon. Can I continue? So the normal distribution looks like this. That is, the PDF of the normal distribution has this functional form. And in this functional form, you have 2 parameters that appear. Mu is the mean, and sigma squared is called the variance. If I tell you these 2 values, you can plug it in and you can evaluate the probability for getting a certain range of x and so on and so forth. Okay. Now, consider the special case where mu is 0 and sigma squared equal to 1. That would mean f of x equal to 1 over square root of 2 pi exponent of minus x squared over 2. Just substituting mu equal to 0 and sigma equal to 1 in this expression. This distribution is given a special name. It is called the standard normal distribution. And this is what we saw last lecture. And the handout here is a plot of, or is a tabulation of the quantity. Handout tabulates 0 to Z1, 1 over square root of 2 pi, exponent of minus beta squared over 2 d beta. What is this quantity? 0 to Z1. Remember this. Tell me what is this quantity? If I write minus infinity to Z1, square root of 2 pi, exponent of minus x squared over 2 dx. What is this quantity? Do you recognize this? What is this quantity? Minus infinity to some value of the PDF. Minus infinity to some value of the PDF. So this is nothing but the CDF, the cumulative distribution function at Z1, or we'll write this is f of Z1. Remember this, okay? We are going to use this, solve the problem. All right, I'm going to keep quiet for 2 minutes, give you a question and ask you to calculate the answer, okay? I want you to calculate from the sheet what is the for a standard normal distribution. Whenever I say that, what you're supposed to think is that the mean is 0 and variance is 1. Calculate the probability of x lying between -1 to +1. Go. This is a possible quiz question right here. Calculate the probability of x taking values between -1 to 1 when the mean is 0. It is centered at 0. This is 0. So you have a bell curve that is centered around 0. What is the probability of x taking values between -1 and +1? Go. You need to get this area under the graph. All the hint you need is right here on this side and here. Do you want to assist or got this? Anybody has an answer or you want to tell me how you will get started? What's your first step? Like
write the integral for both of them.
Okay, so you want to start with the integral form, which is -1 to 1, 1 over square root of 2 pi, exponent of minus beta squared over 2 d beta. Everybody agrees on this? Just drop your pencils. Let's go through the steps. Okay, so you got this or see this in the recording later. You are preparing for the test. All right, so this everybody agrees with. You're okay, right? So this integral right here, you can split it two ways. You can write this -1 to 0 plus 0 to 1. Why we are splitting this is because our tabulation is only for 0 to some value. It doesn't do minus to 0. It doesn't do the left hand side. It does only the right hand side of the number line. Are we cool? Okay. This value is easy to look up. You need to look up where Z1 happens to be 1. Can you look up in your sheet and tell me where it is 1.00? 0.3413. 0.3413. Yes, do you agree with this, everyone? 0.3413. The other integral is 1 over square root of 2 pi exponent of minus beta squared over 2 d beta. What I'm going to do is, let's say gamma equals minus beta. Change of variables. Change of variable, we will introduce a new variable gamma, which is negative of beta, which means d gamma is negative of d beta. You would have done this in your calculus, I'm sure. So if you do a conversion of the limits, the old variable is beta, new variable is gamma. If beta is -1, gamma has to be 1. If beta is 0, gamma is also 0. What's the point of doing that is to also turn this into 0 to something so that you can use the table instead of doing integration. If you, some people might just say, oh, this is an even function, so I'll just split the limits and it's fine. If you already see that, good for you. I'm just breaking it down so that people who don't see it readily can see. Okay, so I have 1 to 0 square root of 2 pi exponent of, I have beta squared, which just stays as minus gamma squared over 2. Wherever d beta appears, I have to replace it with minus d gamma, which is nothing but I have 1 to 0 and a negative sign. I'll write this as 0 to 1 square root of 2 pi exponent of minus gamma squared over 2 d gamma. What is this? What is this value? Again 3413, right? 0.3413. So this is nothing but the first integral is also 3413. So this is 2 times 0.3413 or 0.6826 or 68.26%. Write this thing down because this is the template you are going to keep repeating here on. Does it make sense? If you are not clear, feel free to speak up and ask, okay, so that we can talk it out.
What do you do?
The first integral is 3413. Second is also that. So 2 times 3413. because they happen to be -1 to +1. If not, you would add them separate.
I don't have worse.
Yeah, sure. Instead of -1 to 1, suppose I had asked you what is -3 to 1, then you can't like do 2 times. You have to do add, get one first, get the second first, add them.
Okay.
Okay, assuming you have finished writing this down, drop your pencil, answer this question to me. I asked you what is the probability of x lying between -1 to 1, and it happens to be 68.26. That is, if you do the histogram of these numbers, 68.26% will lie within -1 to +1. That's the interpretation. Your 1 also happens to be the standard deviation. Like when I say -1 to +1, it's like saying minus sigma to plus sigma, because our standard deviation in this case is also 1. Why I'm telling you, listen, this is more important than writing it. Okay. So you between a -1 to +1 lies 68% of the values. It's like saying within ±1 standard deviation, you have 68% of the values in this distribution. Okay. Can you go ahead and compute what is the probability for -2 to +2 within 2 standard deviations? Can you go ahead and do that? And since this function is even, this is almost like writing 2 times the probability of 0 less than or x less than or equal to 2, which is 2 times. You can read the table for 2.00. It's 0.4. Thank you. 4772, or this is 414 carry over 115.95, or 95.44% lies between -2 to +2. That is the common way of saying 95% of the values lie between 2 standard deviations.
But if you want to see between negatives and
Yeah,
just do you would add the value from 1, which is 0.3413 plus.
let's do that.
Okay.
Let's do that. Let's do an example. Thank you for suggesting it. I want to know what percentage of the values lie between probability of -2 to 1. This is -2 to 0, or actually this is -2 to 1 f of x dx, which I'll split as -2 to 0 f of x dx plus 0 to 1 f of x dx. You with me so far? This you can write is also equal to 0 to 2 f of x dx. How? The logic is right here. Same logic. It's an even function, so we can flip the limits and reverse the sign. If you want to do it step by step, go through these steps. Plus 0 to 1 f of x dx. Can you look up what is the value for 2.00 and 1.00? We just did that. 0.4772 plus 0.3413. How much is this? Are you getting this? Like, did you look up and you agree with me that this is 4772 and 3413? Then there's your question right here, between -2 to +1. Okay, I'm going to ask another question, similar question. Can you tell me what is the probability that x will take values from -infinity to 1? I'm not going to do this. You're going to do it on your own and tell me the answer. What will the probability of x taking -infinity to 1 be? What's the probability that x takes values between minus infinity to plus infinity? That is all possible values. 100%. That is one piece of information. The other piece of information is this curve is symmetric about 0. 0 divides them into two mirror images. So if the total area under this is say 1 unit, then half of it is on the left side and half of it is on the other side. You agree with me? That is the second piece of information. I have here minus infinity to not all the way infinity, but to only to 1. That is, I'm starting from way here on the left, coming to the center, crossing the center, and then going up to 1 on the other side. I might as well say minus infinity to 0. If I'm crossing 0, this left hand side contribution is how much? Half, 50%, right? So from here until here, this portion is 50%. You don't have to do sophisticated mathematics to say that. So you have, I'll split this as probability of minus infinity to x to 0 plus probability of 0 to 1. Can I do that? This is nothing but the first value is 0.5. You can write that down in your sleep now. I say that to, my teachers used to say that to show how intimately it is in your head. But some students also sleep in the exam. Okay, what is 0 to 1?
0.3413.
We did that 3 times now, right? 3, 4, 1, 3. So the chance of the value being between minus infinity to 1 is 0.8413 or 84.13%. One more problem like this. What is the probability that the value of x is between 3 to infinity? Everything starting at 3 and to the right of it. What is the probability of x assuming values between 3 or values 3 or above? So if I redraw the bell curve for some clarity, okay, let's say this is 1, this is 2, and this is 3. I'm asking for the area, which is the small sliver right here to the right of 3. Yeah.
0.00135.
0.00135. Before we look at the number, can you also describe to us your process, how you got it?
Just did 0.5 minus 0.49865.
0.5 minus 0.49865.
865.
Okay. Can you explain further what is this 0.5?
That's from 0 to 3.
0.5 is from 0 to 3?
Well, no, it's from 0 to where the curve ends.
Where does the curve end? Infinity. So I told you one information, right? From minus infinity to plus infinity, the area is 1. It's 1 unit. So the left hand side is 0.5, the right hand side is 0.5. Where does the right hand side extend? It starts at 0, goes all the way to infinity. That is this. So this is like writing probability of 0 to infinity f of x dx minus probability of 0 to 3 f of x dx. which is this. This happens to be 0.5 from 0 to infinity. That is, you can look in your tabulation. Look up what is the value of 3.9, 3.09. 3.09 happens to be 0.4990. Okay. If you go further, like 4, 5, and so on, it will keep getting closer to 0.5, never really reaching 0.5 until you are technically infinity. So this table almost stops varying beyond 3.09. That's the point. Okay. So this is 0.49865, which gives you 0.00135 or 0.135%. 0.135%. So if this kind of question appears now, you feel confident, you can solve it. It's about reading this chart. It's about three things actually. First is reading your problem statement and reducing it to a mathematical statement. Your random variable, whatever the context is in your problem, it will say what is the chance of x representing velocity being between -2 to +2 meter per second, something like that. So then you write that down as a mathematical statement. Then you use the chart to get the value. The key really is how you handle the negative values, because positive is easy to handle. Positive is what the chart already gives you. Is the negative values of x that you have to project correctly onto the other side. It's almost like you have the bell curve. Imagine that like it's drawn on a sheet of paper. If you fold it in half, you are projecting everything onto the positive side. So whatever is -5 becomes +5, -1 becomes +1. Okay. Good, good. All right. When it gets good, we invent new problems. That's what we do, right? What is the problem here? Not problem, but we considered a very special case in which mean is 0 and standard deviation or variance is 1. The issue is you won't have such a very special case all the time. Real life will give you mean values which are non-zero and standard deviations which are other than 1. How do you deal with those situations? That is the next challenge. Is the question making sense to you? Okay. So we considered the special case. We'll stop considering special cases. Okay. Stop writing. Listen for some time. We'll continue writing. So if you are given a normal distribution, you are told what is the mean and variance or mean and standard deviation. How do you solve the problem? Like for example, let's say we have the mean value to be equal to 10 and standard deviation or variance equal to 1.2. So if I draw the curve, here is 10, I would draw a bell curve which is centered around 10, not centered around 0. Right? Bell curve is now centered around 10 and the standard deviation or the variance of this is 1.2, not 1. Now I'm asking the question, if this is my x, okay, what is the probability that my x will take values which are between 9 and 12? This is a question where I can say x represents length of a component which is measured, and it has a mean of 10 and a variance of 1.2 because you have a caliper, you measured it 20 times or 40 times, you got a mean value and a variance. Those are these values. Now I'm asking what percentage of the measurements are between say 9 and 11. This is my question. Don't start with your calculator. Tell me what you will do first. How to think about this. We only know We have a handout which does it for a very special case where mu is 0 and variance is 1. You got this tool in your hand, but the problem you need to solve is something else. How do you make an adjustment to use the tool to solve the problem? Sorry, come again. The word is transform. You're right. Concept is right. What you're saying is transform the variable such that, let's say we define z equals x minus mu divided by sigma. We'll call this z. Okay, transform the variable from x to z, where z is defined as, it's like literally you are shifting this distribution to 0. So if this is x, you are shifting this to z equals 0. This is x equals 10 or mu equals 10. You are shifting this to 0. Not only you are shifting the location, you also have to do scaling because this has a width which is 1.2. You want to scale this to something that has a width of 1. Okay, that is what this process is. It involves shifting the location of the mean and scaling the width of the distribution. Okay, write this down. Then we'll continue. In your quiz or your exam, you will not get like a problem saying, get me this problem. I'll write a word problem giving you like a context or a measurement situation, and you will have to translate it from English to math and then do the solving. Okay, so we are doing this shifting. Okay, you have gone from x to z. You then need to make this chart x and z. If x is 9, what will z be? Z will be 9 minus 10 divided by 1.2. Can you tell me what that is? Minus 1 divided by 1.2.
Negative 0.8
Negative 0.83.
continuous groups.
Let's say 0.83 because our table has only 2 digits of precision. Okay. And then 11 is 11 minus 10 divided by 1.2, which is plus 0.83. So first of all, this statement of x assuming values between 9 and 11 is actually a statement of probability for z assuming values between minus 0.83 to plus 0.8. Do you agree with me? And the rest, can you take it home? You want to calculate the value of z, the probability for z taking between minus 0.83 to plus 0.83. Look at this function. This is f of x with x and mu and sigma. If you make this substitution, f of x dx, which is equal to, hold on 1 second, I want to write this down. This is insightful, I think. What is f of x dx? F of x dx is 1 over sigma times square root of 2 pi exponent of minus 1 half x minus mu over sigma squared dx. Right? Just multiplying dx on both sides. So if I make the variable switch z equals x minus mu divided by sigma, this implies dz equals dx divided by sigma. Would you agree? Okay, just differentiating both sides. So this function, I can simply write this is 1 over square root of 2 pi, absorb that sigma into the dx and write this is exponent of minus z squared over 2 dz. And isn't this the table for which you have the values provided to you? Same thing, right? So now go ahead and compute for me what is the probability that z lies between minus 0.83 and plus 0.8. Go. Point 0.5934.
340.
Did you write this as 2 times something? What is that something?
0.2967.
So this is 2 times probability of 0 less than z less than 0.83, which is 2 times 0.267.
967.
Thank you. Not too bad, eh? You see, follow this. You're not feeling lost or anything. So we'll do one word problem. Like if you go to the handout that I posted, anybody has it in their laptop in front of them? I don't want to spend my lecture time like opening the thing, but anyway, so usually what is going to be provided to you is a mean and standard deviation and the fact that your variable follows a normal distribution. More often than not, the mean and standard deviation will be some value other than 0 and 1. It won't be the standard normal distribution. So if I give you a cheat sheet for problem solving, it is to distill the mean and variance of your measurement situation or your problem statement from the problem statement. Number 2, if necessary, or if mean is non-zero and variance is other than 1, if either of them is not the case, effect a change in variable z equals x minus mu divided by sigma. Once you effect that change, convert x1, x2 to z1, z2. x1 being the lower limit, upper limit. That is, if you want to write what is the probability of x1 less than or equal to x less than or equal to x2, this is probability of z1 less than or equal to z less than or equal to z2. Exactly what we did here. Okay, so once you have this written down, like you have here, then use the table. Step 4 is use the table to get the probability value. Welcome back. Doing homework?
Yeah, homework work. Good now, I have a meeting.
All right. This is the cheat sheet for problems in this style. Okay. So firstly, uh, we saw the standard normal distribution, and then we saw how to calculate the probability for any normal distribution, not just the special case. All right. All right, good. Suppose we don't stop when things get easy, right? We invent new problems. The other next step in that. Suppose we do a set of measurements that yields x1, x2, and so on, xn values. You are acquiring voltage or temperature, whatever. You get n values where n is large, usually much greater than 30. Okay. So you get an average or a mean okay, and you get a variance sigma squared, which is 1 over n minus 1, actually 1 over n, I equals 1 to n, xi minus mu whole squared. This is mean and variance. This is your measurement situation in the lab where you have a large number of values taken. You are getting the mean and standard deviation. But one thing you are sure is that whatever this n is, isn't really as large as the original population. N is large, but still n is small compared to the size of the population. Like when I say that, what do I mean? You acquire 1,000 voltage values, but voltage can take infinite number of values. 1,000 is nowhere close to infinity. That is, it can take millions more possible values which you don't sample. Do you see that any act of measurement will get you a certain number of measurements, but will never get you all possible values? That's what a measurement is. Okay. So now my question is, if this is the observed mean, these are both observed values, meaning those that you actually observed. What is the true value of the quantity being measured? If you get 1,000 values and get the average of those 1,000, does it make it the truth? If you get 10,000, does it make it the truth? If you get 100,000, does it make the truth? What is then the true value of this quantity? To answer this, answer one more question for me. Is it at all possible to ever get the true value of some measurement? You can never measure the truth. You can only infer or measure a certain set of values. But what we can say is, here is the measured average or measured mean, and relative to the truth, where does it fall? Is it close to the mean? Is it off base? Is it how much off base? That you can calculate. That making sense? You can get, I can get like a value, and then I can ask the question, what is the true value? Or instead of that, I can ask, what is the probability of finding the true value in a certain range? I'll try to put this graphically here. So suppose, listen, don't write. These things, you don't, it doesn't matter if you write something, but you don't understand what it means. Okay, listen. So you have your mean value, okay, and you have the standard deviation that you measure, okay. Suppose you did like some number of measurements, the truth happens to be here. That is, I'm God and I know the true value. Let's say that. I know the true value, but my measurements are centered around some other value. Graphically speaking, you would say the chance of the truth being in this range is 0. Would you say that? Because it is not at all any, it is what we call off base. Right? Suppose the true value were here. Okay, and if you select a range which is centered around the mean, so this is the true value, this is the mean, there is a chance that the true value lies between, say, this range or between this range and so on. If I select any range, I can always ask the question, what is the chance the true value will fall in this range? I can also do it the other way. I can select the probability. That is, I want to select a range in which the probability of finding the truth is very high, like 95%. Okay, so I'm going to write one more statement here. We define what is called as the confidence interval is the range which contains the true value at a p% probability. We define this interval called confidence interval. When you are in the lab making measurements, you get a mean and standard deviation. That alone doesn't define your measurement. You still have to do statistics to understand what is the confidence interval. So our quantity X here has a mean of mu and a variance of sigma, which came from measurement. Okay, I want to know what is the probability, or I want to know what is the range of X within which the value or the probability of getting this is, let's say, 95%. I'm choosing this is a choice. I want to figure out the range in which this probability or the probability of the truth lying between x1 to x2 is 95%. How do you solve for x1 and x2 is the question. And for simplicity, we'll say, not for simplicity, for symmetry, we'll say x1 is mu minus ci and x2 is mu plus ci. So I have x, I have mu, I have this bell curve, I have ci, or mu plus Ci, and I have mu minus Ci, and I want to say the true value lies between mu plus minus Ci with P equals 95% confidence. That is the meaning of confidence interval. It is an interval in which you can find that you are likely to find the truth with 95% chance. How do we solve for this Ci or the width of this confidence interval? That is the question here. Insofar, in this problem, we told you what is the range of Z and asked you to get the probability. Here we are doing the opposite, telling you what the probability is and asking you to get the limits. Here's a question, okay? Like to help you answer the real question. Can I erase? Sorry. Okay, get your hand out. Answer this question for me. Find the value of x. Okay, find the value of x. Say x naught minus x naught to plus x naught, which is equal to 0.95. Go the other way. That is, find what value of x naught gets you 95% probability. Solve for x naught. That is, just look up through your table and see which gets you a value that is closest to 0.95 with 2 decimal places. So this is probability of 0 less than x less than 2 times probability, or 95 divided by 2, 0.495. What is 495? 1.96. X naught happens to be 1.96. Is
Wait,
around
747. 47. 0.9.
Oh, yeah. 47. Sorry. That is 1.96. Is everybody seeing this? X naught has to be 1.96. Or in other words, probability of minus 1.96 less than x less than 1.96 is 95%. How do you interpret this? 95% of the values are found between negative 1.96 standard deviation and positive 1.96 standard deviation. Right? So 1.96 is the magic value. Come back here. We are asking what is the probability that x between x1 and x2, 95% of the values are likely to be found, or the true value can be found with 95% probability. If you do a variable transformation saying z equals x minus mu divided by sigma. Okay. Z equals x minus mu divided by sigma. So x1, which is mu minus ci, will transform as z1, which is minus ci divided by sigma. No. Yeah, minus ci divided by sigma, and x2, which is mu plus ci, will transform as z2 equals ci divided by sigma. Or I can write, okay, ci divided by sigma. Okay, so probability of x1 to x2 is 0.95 is essentially like writing probability of minus Ci over sigma less than or equal to Z less than or equal to Ci over sigma. This is 0.95. Are you with me so far? Right? You also know, you just found out that probability of minus 1.96 less than or equal to C less than 1.96 is equal to 0.95 right here. So by comparison, Ci is equal to 1.96 sigma. Width of the confidence interval Ci equals 1.96 sigma. You do your experiment, you get a mean. So your experiment or your measurement yields a mean and a standard deviation. All I am saying is the confidence interval is 1.96 times sigma if you are going for 95%. How you would report measurements in a accurate statistical sense is in this way. N trials or observations of a quantity X has a mean, mu, and variance sigma squared. This is the act of measurement. Your 1000 voltage values gets you a mean and a variance. You see that, right? This is no mystery in that. The true value of X is mu plus minus Ci at p% probability, and if p equals 0.95, X true value, it lies between mu plus minus 1.96 sigma with 95% chance. Your own mean value or your own variance by itself doesn't mean anything if you don't account for the fact that X is a quantity that follows normal distribution and can have many more possible values that you saw in your little experiment. That is what this statement is. The true value of X is likely to lie between mu plus minus 1.96 sigma with 95% chance. Can you go back and do if p equals 90%, 0.90, what is the range of true values of X? Mu plus minus something times sigma with 90% chance. It's like asking if you have to solve this you have to solve for x naught less than or equal to x less than or equal minus x naught to x equals 0.90. What is x naught? You mean minus 1.64 to plus 1.6, right? So x naught is 1.64, or this dot is 1.64 sigma. If you want 95% guarantee or probability, the interval is wider. If you want only a 90% guarantee, the interval becomes narrower. If you want only 50% guarantee, can you do that? If P equals 0.50, then X true lies between mu plus minus dot 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 sigma with 50% chance. What is if you have to solve for 50%?
Negative 6.7. 0.67.
0.6, yeah,
So. Well, the measurement you said for 90%,
90%.
I mean, it's that actual number's between 1.64 and 1.65. So wouldn't it be,
It's a matter of degree, so it's like a,
can you just add 1.645?
yeah, you can either interpolate or round off, either is fine. It's like a line call. If you are the umpire or referee, you would call something in, I would call it out. Sometimes judgment call. So is everybody getting 1.64 for 90% and for 50%? 50% I'm seeing 0.67. 0.67 is 0.2486, which if you double is nearly 50%. So this is 0.67. Sorry. Yeah, 0.67. So this is 0.67. All right, here is the question. Why does it matter to know the true value of something? You do a measurement, let's say you do 10,000 measurements. Why do you still want to worry about what the truth could be? Why aren't you satisfied that this 10,000 is the truth?
10,000 is just a small sample of how many options there could be, so you might not actually be getting the true value than those 10,000.
Does everybody agree with that statement? What you measure is only a small subset of the entire possibilities. The other question is, why 50%, why 90%, why 95%? You could presumably do 99%. When do you need more guarantee of something being true, and when are you okay with less guarantee, less probability? I mean, as engineers, you would think your application is driving the level of accuracy or probability that you are seeking, right? What were you going to say?
You're concerned about safety.
Safety. Thank you. So you're talking about safety factors, stuff like that. So if you are a thermal engineer in charge of designing a grill or like a hot plate to make toast, and then you are also a thermal engineer in charge of setting up a mirror that will receive heat from the sun and will make electricity out of it. You're both thermal engineers, but in one case, you are more worried about precision and safety than the other. Which case do you care more about being right all the time? You are designing a spacecraft, a rover, a space shuttle, something, right? Satellite, whatever. A household application comes with lesser stakes and has a wider margin for error. So if you make a griddle and suppose you got the thickness off by like 20%, it's not the end of the world. But if you get it off by 20% in such a high stakes, unforgiving environment like space, the technical term is you're screwed, right? So the probability we choose for the range increases with the level of probability. If you choose 99%, this will be even wider. If you choose 9.999, that is 99.9% guarantee, it will be even wider. If you want 1 in a million, that is going to be very much wider. So this goes up And that probability is generally a function of your states or your importance or your how much margin of error there is in your measurement. Okay, good. So we saw three concepts today: standard normal distribution, working the standard normal distribution for any value of mu and sigma, and then getting confidence intervals. Okay, good. So now we have this. You can go both ways. That is, if I tell you what range of values should X take, you can work out the probability. And if I tell you the probability, you can work out the range of X. It goes both ways. Okay? All right. That's actually pretty much what I wanted to cover related to normal distribution. So you have learned what is confidence interval. The next step, or actually, talk about this topic. So you look at confidence interval. It has several names by which you call it. Some people call it confidence interval. Like for example, if you have a quantity x, and for the mean value, instead of mu, we'll start using x bar, and for variance, we'll still use sigma x squared. Okay, confidence interval, and then number of observations n, and our assumption here is n is pretty large. We'll also talk about the case when you don't make 30 measurements, maybe you make only like 4 measurements. That is a separate discussion which we will do in the next lecture. So this is whatever we discussed today is called the statistics of large data sets. Large is defined as n being greater than 30. And then we'll talk about statistics of small data sets next time. So confidence interval is equal to the value of z, which gets you a certain probability, multiplied by sigma. Zp equals 1.96 for p equals 95%, for example. This confidence interval is also called uncertainty. Uncertainty. When you make a measurement, you report this confidence interval as the uncertainty in your measurement. You have heard of this term before? So when you say I measured a temperature of 100 degrees Celsius plus minus 0.1 degrees Celsius, what we are generally referring is this is the uncertainty. Another name used is error estimate. Error estimate. Okay. You with me so far? You make a measurement, some number of observations, mean, variance, confidence interval. Okay. All right. Can you recall what is Ohm's law? What is Ohm's law? Voltage equals current multiplied by resistance. Right? So if you had a circuit and suppose you had a unknown resistor, you have a measurement of the current through the circuit, and you also have a measurement of the voltage drop across the resistor. If you know the current and the voltage, you can write the resistance equals voltage divided by current. Right? This is not a theoretical calculation. This is, I'm talking about a measurement where you are in the lab, you do a voltage measurement, You independently do a current measurement and then you take their quotient and get a resistance. Okay? Let's say our voltage measurement is 1.00 volt plus minus 0.05 volt, where 0.05 is the confidence interval on the voltage measurement. That is, I did all these calculations and I estimate 0.05 to be the uncertainty or confidence interval. And let's say we have a current which is measured to be 5.42 milliamps plus minus 0.01 milliamp. Same idea. You have a mean and confidence interval. Okay. Then if you calculate, or for simplicity, I'll make this 5.50. I want to calculate the resistance as a mean value plus an uncertainty that goes with it at 95% confidence. At the same level of confidence. How do I do this? This is the question. So this has a mean value, I'll call that R bar, and this has an uncertainty which I'll call UR. Mean, uncertainty. Uncertainty is the range about which the true value is likely to be found, or another word for confidence. Mean is pretty easy. You just take the mean value of the voltage divided by the mean value of the current. So that would be 1.00 volts divided by 5.50 milliamps, which gives me, can you tell me this? 1000 divided by 5.50. I'll actually make this simpler. Make this 5.00. This will be 200 ohms. How many decimal points should I include? How many significant figures are there?
Two decimals. Or no, you don't need any.
How many significant figures?
30.
Three. How many significant figures?
3.
Three or one?
1.
200 is one, the way you have written it, right? But the understanding is if this were say 5.50, you would get like 195 ohms, in which case you have three significant figures. So even though this is written 200, this is understood to have three significant figures. Okay, so 5.00, 200 ohms. You with me so far? Mean value. What about the uncertainty? The uncertainty in your R resistance is coming from two sources. It's coming from your uncertainty in the voltage and also in the current. If you had both of them to be perfect measurements, like this is 0, then your uncertainty is also 0. So instead of dragging this out as a derivation or something, I'm just going to give you a formula. The uncertainty in R is the partial derivative of R with respect to V multiplied by the uncertainty in V squared plus the derivative of R with respect to I, the uncertainty in I squared, the whole thing squared. What is this? Partial R over partial V is 1 over I. Right? I just need to take this and differentiate. Partial R over partial I is minus V over I squared. Right? Minus V over I squared. So this is a little messy, okay? But here is a trick that I'm going to pull, not a big trick, you don't have to be scared. So UR divided by the mean value of R is equal to uncertainty in R divided by uncertainty in B multiplied by uncertainty in B divided by R. Yeah, divided by R, which is just uncertainty, it's just B. No, actually, no. I just substitute it here directly. So uncertainty in R is square root of, what is this? 1 over I. And what is this? This is UV. This is UI times 0.05 volts squared plus minus B over I squared times 0.01 milliamps squared. So you can complete this at home. We are almost out of time. Substitute the value of I equal to 5.00 milliamps. Substitute the value of V equal 1.00 volts and get me the uncertainty in R, which should be some value of ohms. So four topics we saw today, and for the quiz, okay, standard normal distribution, any normal distribution, confidence interval, and then uncertainty estimation. These are the four concepts we saw today. And if I also add discrete distributions from last lectures. Okay. For Thursday's quiz, hold on, I'm not yet done. For Thursday's quiz, whatever I cover on next Tuesday, I'm not going to ask that. That will be covered in the exam. Until whatever I taught today, we are covering in next Thursday's quiz. The topics that I want you to really study for at least the quiz, these three, and out of this, mainly boson. So this is 1, 2, 3, 4 topics, 2 problems. I'll keep you guessing with 50% chance. Okay, 4 topics, 2 problems for the quiz, and for the exam, everything that I say is fair game. All right, we'll meet on Tuesday. Thank you. Oh, just one more question. If I hold a additional problem solving session like 90 minutes, would you guys be interested? Just do examples, no teaching, like just examples.
Outside of class
Outside of class.
and explain that.
Okay, I need all of you to email me some preferred timings that will work for you. Depending on how much response I get, I will do it.
You could record yourself. It's a problem with those cameras.
I hate doing that by myself. If I don't have an audience, sorry, I'm not doing it.